Welcome back to another lecture from organic chemistry, and thank you very much for watching this lecture video. And this lecture, I'm going to go through physical and some chemical properties of alcohol. The first one, it will be the miscibility of alcohol with water. Alcohol, it has the OH group, and we know OH is capable of building technically or getting involved in hydrogen bonding because H has a positive charge and O it has negative charge. And remember, O it has two lone pairs. So it's capable of building hydrogen bonding. And OH, it will be the hydrophobic head or region, and because it can actually loves water, and the non-polar area or the carbon that's attached with some hydrogen or some carbons, we call it hydrophobic region. And the longer the chain is, the higher hydrophobic character you will see. That means the solubility will go down by increasing the length of the chain. And in some cases, we want it actually to be longer chain. Why? Because I'm using it to get rid of grease from a fabric. So many detergents do have a long chain, but you have to keep in your mind, longer chain means lower solubility. So does it mean that that the detergent is going to be sitting on my clothes, and when I dry it, I might see some white spot? Yes, it's possible. Okay, it's possible. So you need to design a stronger and hydrophilic group that is capable of pulling entire of this change and get it dissolved in water. And many detergents, they work on that head, and they will try to design, like a head that it has a plenty negative charge, so it can establish interaction with water. And alcohol also, we use them as antibacterial agents because alcohol are capable of dissolving, grease. And in this case, as you see, it says the best potency, or the best actually efficiency for alcohol to work as like antibacterial is when we have 8 carbons, and higher than 8 carbons it will go down. In fact, if you remember correctly, like during COVID, we had the issue with alcohols, and actually finding alcohols. The reason for it, because many of these hand sanitizers are made of 80% alcohol, ethanol, 80% ethanol, and 20% water, or 75 isopropyl plus 25 water. And change, or like the change or number of carbons that we're talking about, between 2 to 3 carbons. And 2 to 3 carbons, if you have only 2 to 3 carbons, the boiling temperature is not going to be high. That means when you actually rub those stuff on your hand, very soon your body is going to warm them and it will evaporate them, and that's not going to be issue. Okay. And when it comes to hand sanitizer, remember that any cell, it has a shell that is protecting it from a germ that coming inside the cell, or actually holding the cell components, and it will trap them and it will stop them from going outside. Now, imagine this is a bacteria and you want to use actually alcohol to kill it. Alcohol is going to put its non-polar change here. And remember, this is going to be the polar head. And the polar head, okay, very soon, okay, it can be actually pulled by water, and the more the more like alcohol molecules diffuse in that chain, in that actual layer, and the higher, like the bigger the gap will be. Which gap I'm talking about? Technically, you're gonna build a pathway. Very soon, you will dissolve those, grease. You pull them, you dissolve them, and you will open a pathway. And now when you have a pathway, and some of the cell component, they go out, or we can have white plaques, they come inside the cell and they will go after the cell, and they can actually decompose the bacteria. Now, when it comes to chemical properties, and we said alcohols are not strong, they are not actually strong acids, and alcohol the alcohol, whenever they react with, like some bases, they can give actually H to them. But the base has to be strong enough to pull hydrogen from it. Again, I said this is going to be a weak acid. So you need to have a strong base to pull that hydrogen from it. And one of the bases that we use is a hydride. And hydride is a hydrogen with a negative charge on it. And so this is going to be a strong base. Strong base, it will take hydrogen from alcohol and it will turn it to this species. We will have oxygen with the 3 lone pairs. So this one will be -1. And also we get half a mole from hydrogen gas. Okay. And or you can say I started with 2 mole from like alcohol, 2 mole from hydride, and then in that case I get 1 mole from hydrogen gas. Okay, this one will be a conjugate base. And okay, again, I said because alcohol is a weak acid, this is going to be a strong conjugate base. What does it mean? It means less stable. And if it's less stable, it will be more reactive. So keep this one in your mind that they are really reactive. Okay. Another way to create, create the conjugate base or alkoxide, okay, alkoxide is to treat them with metals like sodium, potassium, or lithium. Why those metals? Because if you write the electron configuration for example, sodium is equal to neon and then 3s1. The last layer, it has 1 electron. And if they lose that electron and turn it, for example, to sodium +1, in that case, you get 1s2, 2s2, and then you get 2p6. Last orbital, it will be fully occupied, and the system will be stable. And so that's the reason they are strong reducing agents. They want to give up actually their electron. So they will give electron to hydrogen, and they will turn it to, 2 moles. Let's say this compound will have a negative charge, and then we get 1 mole of hydrogen gas. And of course, we're going to have sodium, and sodium with a plus charge. We will have 2 sodiums, and those 2 sodiums will cancel the 2 negative charges that we have. Again, alkoxide are not stable, okay? Because they are not stable, and they will be very reactive, okay? And how do we create alkoxide? Alkoxide, we said we react them with metals like lithium, with lithium, potassium, or sodium. That's one way, or react them with a strong base, pull the hydrogen from them, and you will get that base. Okay, now, and the first one, I have a carbon with a negative charge. This one is nitrogen with a negative charge. Here I have oxygen with negative charge. Last one, we say, let's say fluorine with negative charge. Okay, so again, -1, -1. This is -1, and that one also -1. I know electronegativity to the right side of periodic table increases. Down in any group, electronegativity decreases. Okay, so fluorine has the highest electronegativity. That means fluorine is more capable of handling the negative charge than oxygen or nitrogen or fluorine. So I'm gonna say F -1 is more stable, okay? It's more stable than oxygen, okay? And then F, I have to say this one, F, it has also a bit some unique character. So like because the small size is too small, sometimes it will building too much repulsion, but let's not go in and we talk about that one. So I'm going to say F is more capable of handling negative charge than nitrogen, than oxygen, and then nitrogen, and carbon. Hey. So if I know that F is more capable of handling the negative charge, so I'm going to say HF, it will be a stronger acid than, for example, H that attached to oxygen or H attached to nitrogen. And that's true. And this acid is stronger than water, and this one is stronger than ammonia, and stronger than methane. Okay. Now, so we said anything that stabilizes the conjugate base, it will increase the acidity. Okay, it will increase the acidity, anything that stabilizes them. And that's going to be nature of the atom by itself. Okay, if your atom is more electronegative, is more capable of handling the negative charge, so the acidity will go up. And something that I want to actually mention it before we move to next subject is, so we got this. We got R attached to, let's say, oxygen. Oxygen has the negative charge, and we call this one alkoxide. Alkoxide. And one example, if, for example, you go methane, attach it to oxygen, -1. Name for this one, it will be methoxide. Okay. And if it has negative charge, you call it methoxide. But the group by itself, if you have this and this one now is attached to somewhere, this one we call it methoxy. Okay, so methoxy when it's a substituent. Methoxide when it has a negative charge by itself. Okay, and so technically you can call this one alkoxy. Alkoxy group, they will be behaving as a substituent. Okay, now we said stuff like this, they can react with, say, they can lose hydrogen and they will turn to such a species. Okay, this is going to be the acid, so that one it will be the conjugate base. The conjugate base, it has negative charge. This is a strong base, so call it strong base because we started with weak acid. If it's a strong base, it can handle E2 chemical reaction, so it will be a strong actually reagent for E2 chemical reaction. Also, because it has a negative charge, it will be a strong nucleophile. And if it's a strong nucleophile, it can easily handle SN2 chemical reactions. So alkoxides are strong bases, so they can easily run E2 chemical reaction, and also they are strong nucleophiles. That means they can handle SN2 reactions. Okay, now, and what will happen if we have a cyclic compound and there is an OH attached to it? Still, it will be alcohol. And for example, if I remove H from it, I get this species with a negative charge plus hydronium ion. This is going to be an alkoxide group, but a cyclic version of it. Now, if you remove H from phenol, okay, phenol is technically alcohol, but it is attached to a ring, and the ring is, it has a conjugate system, or it has 3 pi bonds there. And if that one happen, we get this compound. We get O. It has 3 lone pairs. This is going to be -1. Okay, similar to the top one, we have 3 lone pairs, and also we have a 3 pi bond there, plus hydronium ion. Anything that stabilizes the conjugate base, it will increase the acidity. Okay, so now let's say we got this one, and this one, it has -1 charge, and I have 3 pi bonds there. Okay, this is going to be the first position, second, 3, 4, 5, 6. Okay, if you generate a negative charge on a phenol, you can actually distribute that negative charge and put it on the second, fourth, or the sixth position. So, and how do we do it? We will share this lone pair with the ring, and then this is going to happen. We will have a double bond. Now we get a negative charge there. That's one. Another possibility is, okay, move this double bond there. If you move the double bond here, okay, and let me erase that one. Okay, I move the double bond there, and now what will happen? I get the double bond. Forgive me. I get a negative charge here. Now I have a negative charge here, and another double bond there. Okay, let's move the negative charge, and like sorry. Let's move the negative charge here, and if I use that negative charge to make a double bond, okay, then I will get this. So I got double bond here, and the negative charge will go there. Okay, so I got 1, 2, 3, and 4 resonance structures. Let's highlight position of negative charge. That's a negative charge sitting on oxygen. 1, then 2, 3, and that's the 4th one. I got 4 resonance structure, and that system is going to be super happy. So I'm going to say pKa of phenol, the pKa for phenol is going to be higher than the cyclic and the alcohol that I mentioned at the top, or cyclohexanol. Okay. Another one is the induction effect. If you have a withdrawing group, that withdrawing group is going to stabilize the conjugate base. So in this case, when we get a negative charge, there's nothing there actually to stabilize it. In fact, we have electron donating group. This group is going to give electron to oxygen. It will exaggerate the negative charge, so it will be less stable. It will be less stable. But how about the chlorine? If we replace the hydrogen by chlorines, because chlorine has higher electronegativity, it will pull electrons. And so instead of giving electron, we are trying to steal electron this time and give them to chlorine. And when we get the conjugate base, when we get this one, because we have 3 chlorines, those chlorines are going to help us to pull the electron density in this direction and give them to the chlorines. And that's going to make the system more stable. So I'm going to say this one is a stronger acid than ethanol. And okay, last one, it will be the solubility. Okay, anything that's reduce stability of the conjugate base, it will make the acid less, okay, less actually acid or weaker acid. Now, when I look to this molecule looks like linear one. I can draw it as a linear molecule. Okay, I have a negative charge here, plus say H plus, but this one, it has some substituent here, as you see. Okay, when one molecule trying to reach this through hydrogen, it's gonna fill those, substituent. Well, with ethanol, we can easily reach it. So I'm gonna say the solvation or interaction of solvent with the conjugate base, when it's linear, it will be easier. So this one, I'm gonna say the solvation or interaction between solvent and the conjugate base on ethoxide is gonna be stronger. Stronger interaction. And I have 4 solvent molecules there. So what will happen? This one will be more stable. Okay. And this one, it will be less stable. If it's less stable, it will be weaker acid. So that means ethanol, it will be stronger acid. Okay. And this is going to be end of this lecture. And thank you very much.